Hello students, and welcome to the third part of the topic equilibrium. We are on question number 11. Now let us see over here what is indicated in the question. A 20-liter container at 400 Kelvin contains carbon dioxide at a pressure of 0.4 atmospheres. Okay. And an excess of strontium oxide. What is mentioned over here in the bracket is to neglect the volume of the solid strontium oxide. Now the volume of the container is decreased by moving the piston. Okay, what they want us to find is the maximum volume of the container when the pressure of carbon dioxide attains a maximum value. Okay, so currently the pressure of carbon dioxide is 0.4 atmospheres and the volume of the container is 20 liters. What they want us to find? Maximum volume of the container when the pressure of carbon dioxide will be maximum. So now we can say that SrCO3, it is reversible with SRO and CO2 from the reaction that is given over there. Let us say that Kp will be the pressure of carbon dioxide, which is given to be 1.6 atmospheres. Let us assume this to be the maximum pressure of carbon dioxide. Now from ideal gas equation, okay, from your ideal gas equation, everybody knows that PV is equal to nRT, and in that respect volume becomes nRT upon P. Let us have this as equation number 1. Now we all know that equilibrium has not been achieved in this given question. Equilibrium has not been achieved. So because equilibrium has not been achieved, we can say that the value of n is constant because the container is sealed. So you can mention over here that the container is sealed. Okay, container is sealed and equilibrium is not achieved. Now because equilibrium is not achieved, container is sealed, so therefore n is a constant. Now if n is a constant for the second condition, the expression becomes PV is equal to nRT from ideal gas equation, and we can say that again now your n is going to be PV upon RT. But what is the value of pressure given over here? 0.4 atmospheres. What is the volume of the container? That is given 20 upon RT. Now this happens to be the expression, that is the second expression. So what do we do? What do we do now? We substitute the value of n in the second expression in the first expression. So what will be the expression for V? Now substituting 2 in 1. What do we get? Substituting 2 in 1, what do we get over here is that V becomes equal to 0.4 into 20 upon RT. You're getting that? This will remain in bracket into RT upon 1.6. So what do we notice over here? RT gets cancelled. When you simplify this, we come to know that the final value for the equation over here will become 0.4 into 20. So this can be written as 4 into 2 upon 1.6, for which the answer turns out to be 5. So in that case, your answer for the question is going to be option D, that is 5 liters. Now let us have a look at question number 12. The first and the second dissociation constant of an acid H2A are 1 into 10 raised to minus 5 and 5 into 10 raised to minus 10 respectively. The overall dissociation constant of the acid will be, now here you have the four options, that is 0.2 into 10 raised to 5, 5 into 10 raised to minus 5, 5 into 10 raised to 15 and 5 into 10 raised to minus 15. what we'll be doing over here is that H2A is the acid that is given to us. Let us first try to dissociate it once. We get H plus plus HA minus. Okay, now let us keep this as K1. K1 is the concentration of H plus into the concentration of HA minus upon H2A. The value for this is given to be 1 into 10 raised to minus 5. Okay, now the next thing after that is the second dissociation. So the second dissociation is going to be of HA minus, that will dissociate to give you H plus and A minus 2. Okay, it's already carrying a minus charge, so over here it cannot be just minus 1, it will be minus 2. So the K2 value over here becomes again H plus into A2 minus upon H2A. Now the value for this is given to be 5 into 10 raised to minus 10. What we are supposed to find? The overall dissociation constant for the acid. So let the overall dissociation constant over here be K. K will be equal to K1 into K2, which will work out to be 1 into 10 raised to minus 5 and 5 into 10 raised to minus 10. So this will be 5 into 10 raised to minus 15. Works out to be a very simple question. Your answer for the question will be option D. Now let us have a look at question number 13. In a saturated solution of a sparingly soluble strong electrolyte AgIO3, molecular mass is given to be 283. The equilibrium which sets is AgIO3 reversible to give you Ag plus and IO3 minus. So that is your equation, that is AgIO3 in a reversible process. It is giving you Ag plus plus IO3 minus. Now the solubility product constant Ksp for AgIO3 at a given temperature is 1 into 10 raised to minus 8. What is the mass of AgIO3 contained in 100 ml of its saturated solution? Slightly complicated. Pay attention over here. We have the Ksp value of AgIO3 which is given to be 1 into 10 raised to minus 8. So अभी सबसे पहले तो Ksp का expression हो जाएगा concentration of Ag plus and concentration of IO3 minus. So the Ksp value will turn out to be S into S, which will be S square. So the value of S will be root of Ksp, because Ksp का value दिया हुआ है. We have the value of Ksp. So solubility will be 1 into 10 raised to minus 8. That is 1 into 10 raised to minus 8. And which will turn out to be 1 into 10 raised to minus 4. That will be the solubility. But what do they want you to find out? They want you to find out the mass of AgIO3 contained in 100 ml of the solution. So what we'll have to do is that this value of solubility is for moles per liter. This value is for moles per liter. We need to find out the mass of AgIO3 present in 100 ml. So what is that mass going to be? We have the molecular mass given to us, that is 283. 283 grams per mole is the weight of AgIO3. So what do we do now is a very simple thing. You have the solubility value, that is 1 into 10 raised to minus 4, which will be multiplied with the molar mass of AgIO3, that is 283 grams. Okay, and this is for the value that we have to find out is for 100 ml solution. So you multiply this by 100 and you divide this by 1000 to get the mass of AgIO3 in grams present in 100 ml of the solution. So the value turns out to be 2.83 into 10 raised to minus 3, because this is 10 raised to minus 4, this is 10 raised to 2, so you will be left with 10 raised to 2 in the numerator, which will make the numerator as 2.83 upon 1000, which will turn out to become 2.83 into 10 raised to minus 3 grams present per 100 ml of the solution, and your answer will be option C in that case. Alright students, let us have a look at question number 14. It says the species acting as both Bronsted acid and base is. Now 4 options are HSO4 minus 1, Na2CO3, NH3 and OH minus. Now everybody knows that over here ammonia, if we talk about ammonia, it's a strong base, and it's Lewis base because nitrogen in ammonia donates the lone pair of electrons. Okay, talking about OH minus is an acceptor. It can accept H plus ions, so even that does not fit into the criteria of Bronsted acid as well as a base. Okay, and Na2CO3 is a salt, so Na2CO3 again, it's a salt. It will give you 2 moles of Na plus and carbonate ion. So these 3 options does not fit into the criteria, so the option that works out to be is HSO4 minus 1. It can donate a H plus to become H, to give you H plus plus SO4 minus 2, as well as it can accept an H plus to become H2SO4. so it can donate a H plus as well as it can accept an H plus. So this is what makes it Lowry Bronsted acid as well as a base. So in that case, your correct answer turns out to be option A. Now let us have a look at question number 15. Which equilibrium can be described as an acid-base reaction using the Lewis acid-base definition but not using the Bronsted-Lowry definition? Okay, so now over here we have to keep in mind 2 things. Lewis, okay, which is the option which is satisfying the Lewis criteria but not the Lowry Bronsted definition. So we have to look out for gain and loss of lone pairs with respect to Lewis. Lewis is for lone pair, and Lowry and Bronsted, we saw it in the previous question just some time back. Lowry and Bronsted is with respect to the H plus ions. So now if you look at the options that are given to you, ammonia H2SO4, it is with respect to H plus. Ammonia is accepting a H plus from H2SO4 and giving you ammonium ions and sulfate, so it is satisfying the Lowry Bronsted criteria, okay, but not the Lewis criteria. Ammonia with acetic acid over here, again the acetic acid will dissociate into acetate ion and H plus, and the H plus is going to ammonia to give you ammonium ion. Okay, there is water and there is acetic acid. Acetic acid is again dissociating to give you an acetate ion and an H plus, and the H plus is going to water to give you a hydronium ion. So it's quite clear in the first 3 options there is an exchange of H plus ions. H plus is either lost or it is accepted, and thereby the option A, B and C will not fit into the criteria of Lewis because they are satisfying the Lowry Bronsted definition. So now option D, let us have a look at the option D. You have hydrate of copper carrying a charge of -2 and ammonia, and it is changing into cuprammonium ion and water. So here we can clearly notice that the option D, it involves the loss and gain of electrons. Okay, water is forming a coordinate bond with the copper by donating the electrons. So in that case, your option D will turn out to be the right answer, which will be acid and a base reaction with respect to the Lewis theory. Now let us have a look at question number 16. Which one of the following statements is not true? pH plus pOH is 14 for all aqueous solution. Everybody knows this is a general standard rule that the pH plus pOH is 14. pH of 1 into 10 raised to minus 8 molar HCl is 8. Let us have a look at the other options. 96,500 coulombs of electricity when passed through a copper sulfate solution deposits 1 grain equivalent of copper at cathode. It should be 1 gram equivalent. Okay, it will be 1 gram equivalent of copper at cathode. And the conjugate base of H2PO4 minus is HPO 2 minus. Now quite obvious that the pH of 1 into 10 raised to minus 8 molar HCl solution is 8. Dear students, everybody knows that if we talk about acidity and basicity, if this is 0 and if this happens to be 14 with 7 in the center, acids range between 0 to 6.9 and bases from 7.1 to 14. HCl is acid, and acid can never have a pH value of 8 because 8 is a pH value that is basically applicable to bases. So in that case, which of the following statements is not true? Your option B turns out to be the answer, which is not correct. And even if we go to solve it numerically, we will notice that 10 raised to minus 8 molar is the concentration of aqueous HCl. Okay, because they are talking about the pH of 1 into 10 raised to minus 8 molar HCl. So that will be anyways in water. So the remaining part of the H plus ions will be contributed by the water, that will be 10 raised to minus 8, and the other part will happen to be water will be contributing the other part of the H plus ions. So it will anyways make the pH value drop under 7. So in that case, pH of 1 into 10 raised to minus 8 molar HCl is 8 is something which will not be the right option. So the answer is option B. Now let us have a look at question number 17. How many liters of water must be added to 1 liter of an aqueous solution of HCl with pH 1 to create an aqueous solution of pH 2? So the pH is 1, we want the pH to be 2, we have a 1 liter solution. How much more water? Okay, so we are increasing the pH value, so we are increasing the dilution, so we are decreasing the concentration. Now if pH is equal to 1, so in that case the H plus ion concentration will be 0.1, and if pH value is 2, so in that case the H plus ion concentration will be 0.01. so let this value will be M1 and let this value be M2. We have been given that the pH 1, the volume of the solution is 1 liter. So let us say that V1 is equal to 1 liter. Students will be applying a very simple formula over here. We are all aware M1 V1 is equal to M2 V2. So in that perspective, when we solve the question, we get the answer as for V2, we'll be getting the answer as 10 liters. So the final volume, because it's a very straightforward conversion, you will notice that your M1 will be 0.1, V1 is 1, M2 will be 0.01, V2 is what we have to find. So it will be a very clear substitution of 1 into 0.1 is equal to 0.01 into V2. So V2 turns out to be 10 liters. So the amount of water that has to be added will be you already have a solution of 1 liter, so it will be 10 minus 1, that is 9 liters of water will be added into the solution. So your answer will be option D. Now let us have a look at question number 18. Zirconium phosphate Zr3PO44 dissociates into 3 zirconium cations of charge plus 4 and 4 phosphate anions of CHArG charge minus 3. If molar solubility of zirconium phosphate is denoted by S and its solubility product by KSP, then which of the following relationship between S and KSP is correct? They want us to solve this equation. So now zirconium phosphate Zr3 PO4. Now if this dissociates, what do we get? We get Zr plus 4, charge of plus 4, and phosphate anions PO4, okay, of charge minus 3. So we are basically getting 3 zirconium ions and we are getting 4 phosphate anions. Now if you see the charge, it is 3 into plus 4, so that is plus 12, and 4 into minus 3, that is minus 12. Now if we go on to express the solubility product for this thing, it will work out to be 3s cube, okay, and it will work out to be 4s raised to 4. So in that case 4s raised to 4. So when we simplify this thing, it will work out to be 27s cube, and 4 raised to 4 will again be 256 s raised to 4. Now on simplifying this expression further, if we notice the 27 multiplied with 256, it will give us the value of 6912, and the power of S will turn out to be 7, and that will be the value for the KSP. So if we talk with respect to the solubility, so it turns out to be KSP upon 6912, and the whole will be raised by 1 upon 7. So this is your answer for the question number 18, that is option C. Alright, now let us have a look at question number 19. Which one of the following arrangement represents the correct order of solubilities of sparingly soluble salt? There is Hg2Cl2, mercurous chloride, chromium sulfate, BaSO4 barium sulfate, and chromium chloride CrCl3 respectively. Now what we'll be doing over here is we'll be preparing the equation for all of these. If we talk about Hg2Cl2, it would reversibly give us 2Hg plus 2Cl minus. So in that case it would be 2s over here and 2s over here. So the KSP turns out to be 2s square and again 2s square. So there is 4s square and 4s square, 16s raised to 4. For Cr2SO4 thrice, it will turn out to be 2Cr plus 3 plus 3 SO4 minus 2. So it is 2S over here and 3S over here. So the KSP would turn out to be 2S square and 3S cube, which will eventually turn out to be 4S square and 27S raised to 3. So it is 108S raised to 5. For barium sulfate BaSO4, the value will be Ba plus 2 plus SO4 minus 2. So it would be S and S. So the KSP value over here would be S square. And for chromium chloride, it will turn out to be Cr plus 3 plus 3Cl minus, so that is S and 3S again. So the KSP value will be S and 3S cube, so that is 27S raised to 4. Now if these four values are being compared with respect to each other, so that is for Hg2Cl2 we have 16S raised to 4. For chromium sulfate we have 108 S raised to 5, and for barium sulfate we have S square, and again for chromium chloride we have 27 S raised to 4. If you compare these four values, you will understand the correct order for solubility happens to be option B, where barium sulfate with a value of S square will be the greatest one, followed by Hg2Cl2, which is 16S raised to 4, and then you have chromium chloride with a value of 27S raised to 4, and then the least one, that is chromium sulfate with the value of 108S raised to 5. So comparatively option B will stand to be the correct option in the question. Now let us have a look at question number 20. It says that at constant temperature, the equilibrium constant Kp for the decomposition reaction of N2O4 into 2NO2. Okay, so ये जो इक्वेशन है इसका Kp एक्सप्रेशन कैसा बनेगा? इट विल बी NO2 square upon the concentration of N2O4 is expressed in terms as 4x square p upon, so it is also expressed as 4x square p upon 1 minus x square, where p is the pressure and x is the extent of decomposition. Now which one of the following statements will be true? We are talking about Kp. It is a gaseous reaction, so the equilibrium constant with respect to pressure, because it is a gaseous reaction. P is the pressure and x is the extent of decomposition. Which of the following statements is true? Kp increases with increase in pressure. Remember students, we are talking about equilibrium constant. There are very few terms and very few factors on which the value of Kp depends in any reversible reaction, and for that matter even the value of Kc depends on very few factors. Kc is with respect to equilibrium constant for any solid or liquid reaction. Kp is with respect to any gaseous reaction. So over here the options are Kp increases with increase of pressure, Kp increases with increase of x, that is extent of decomposition, Kp increases with decrease in extent of decomposition, Kp remains constant with change in P and X. Now P and X, extent of decomposition and pressure, these are two interrelated terms, and because they are interrelated they will balance out each other in such a way that Kp will remain constant. Okay, so remember this thing, that if the pressure will increase beyond a certain limit, the extent of decomposition would go down, or if the extent of decomposition would increase beyond a certain limit, the pressure would go down. So these two factors, the extent of decomposition and the pressure, will balance out each other to keep Kp, that is equilibrium constant, as constant value. So answer D will be your correct answer for this question.